This is Algebra 2 a trig, 1b, point 1b. We're talking about quadratic functions, specifically in vertex form. So we know that vertex form has an a value, an h value, and a k value. Those are the parts that we need to make an equation. The quadratic functions have tables with a constant second difference. We've talked about second difference before, and we'll go over that here with this table. The vertex is the point between the matching pairs of y values. So we come down here and we're looking for a matching pair of y values. There's your matching pair of y values, another matching pair of y values. If the table went even longer, those would match, and then those would match. So this is your vertex, because it's in between the matching pair of y values. The vertex will be, let's see, the vertex will be the h and k in the equation. That's your vertex. And the a value is in the equation is half. This might be new to you. Is half the value of the second difference. So let's talk about the second difference. You did this last week. To determine our differences, we always start with the x value that's the smallest. Right? Don't start from larger x's and work backwards. Then you're going to say it's coming down. All right? We're going to start with our smallest x. From 11 down to 7.5, we would call that, it's going down by 3.5. And then our next two numbers would be negative 2.5 and negative 1.5. And then only negative a half. Then it goes up a half. It goes up 1.5. And if the table kept going, we would pick up those other amounts. Is that difference all the same? That's called the first difference. The first difference. If this was a linear table, then those would all be the exact same number. Then it makes a straight line. If they were all the exact same number. It's an absolute value if half of them are the same number and then the other half are the same number. With opposite signs, then that would be absolute value. These are not that. So let's see. Let's check it again. That distance working from a negative 3.5 to a negative 2.5 is positive 1. Positive 1. 1 to the right, 1 to the right, and 1 to the right. Now we have a constant second difference. So our second difference is the same. Now what we've learned up here is that the a value of the equation is half the value of the second difference. So the a value is going to be half the 1. So the a value in this case is going to be a half. Let's see if that makes sense. You can do it like this. The y value, if this is the vertex, this should go over 1, up 1. That's over 1. And the y value should grow by 1, but it's only growing by a half. The y value, or actually the x, from the vertex is going over 2, and the y value is only going up 2. It should be going up 4. It's only going up 2. So it's going up half the distance. So that helps reinforce that this is a half. So our vertex is 2, 3. Our equation should always start out as y equals a, x minus h squared plus k. That's our equation. Don't say that you look at this and don't know what the equation is. You got to find the little pieces. Break it down into the little pieces we know. We know that the h value is part of the vertex. So this is going to be a minus 2 plus k, which is 3. So we have part of our equation. We have a choice here. We have an algebraic method that we can use to help us figure out a. But we've already found a. True. You can use that method. If you like second difference, you can use that method. But let me show you another one. You can use any point along the path. Just don't use the vertex. Any point along here, 4 and 5. This one looks really good. 0 and 5. That's a good one to use. So I'm going to use 0 and 5. So my x value, my y value. My y is 5. I don't know my a. My x is 0. Subtract the 3. That gives us 2. 0 minus 2 is negative 2 squared. Square the negative 2. And divide by 4 to get the a by itself. What did we get? Reduced is going to give us a half. So a is a half. You can do it using that method. I would love to have you showing your a value using algebraic. You're welcome to use second difference if you like. Either method. There are times where this is more appropriate. If you don't have all of the points to find the second difference, this is a way you can find it, the a value. So now we know that the a value is a half. We can write the rest of our equation. There it is. So we know the domain of all quadratics is all real numbers. That's because you can plug in any number for x into the equation. That's why it's called all real numbers. You can plug in any number you want. What type of answers can we get? If you look at the table, 3 was the smallest number we could get. And then the values got bigger. They got bigger because the a was positive. So we're going to be greater than or equal to 3. And of course, the end behavior, as x approaches negative infinity, our y value is doing something. And as x approaches positive infinity, our y value is doing something also. So this is end behavior. What are the values that go in the blank? Notice your table. When you start to go to smaller x's, the y value keeps getting bigger, and it keeps getting bigger forever. So that's to positive infinity. And then to the right, it starts to grow. So that's positive infinity. A quadratic is always going to point in the same direction. They'll both get bigger, or they'll both get smaller. If it has a negative a, they'll both get smaller. So let's try it down here with another table. I'll put the pencil down, you pause the video, and you work on your second difference. Give that a try. So we'll come back and we'll give this a try. We always start with x's that are small. I notice that this grows by 9. This grows by 3. This is going down by 3. This is going down by 9. This is going down by 15. And down by 21. Those are not all the same. That's the first difference. So if we test it again, we see that we go down by 6. From 3 to negative 3 again is down by 6. Down by 6. Down by 6. And down by 6. So my second difference is my constant. That shows that this is a quadratic. So my A value is going to be half of my second difference, which makes it negative 3. My vertex is in the middle of my common y values. So my vertex is right here. So if my vertex is negative 3 comma 4, my equation's going to be negative 3 x plus 3 squared plus 4. My axis of symmetry is going to be my h value. Don't make the mistake and change the sign. Think about what it means. It has to follow where your vertex is at. The equation is going to be opposite of what the vertex looks like. Your transformation, we have a reflection over the x-axis because the a value is negative. If you take a look from your vertex, all the y values get smaller and smaller, so that reinforces that. We have a vertical stretch by a factor of 3. We can call it 3. I'm okay with negative 3. We've kind of talked about it different ways. It's a multiple of 3. If we've talked about the reflection as using our negative, then this is multiplying the values by 3. And translated, left 3 and up 4. That would be our transformations. That's our compare. Just like we've done before. And then we can finish up with our two equations. Create a quadratic function. So there it is. They're telling you what type of equation to make. You know you're going to be making a x minus h squared plus k. It has to be quadratic. That is narrower than the parent function. To be narrower, you need an a value that is greater than 1. And we can call it an absolute value of a because negative 3 would also be narrower than the parent function. It has a domain of all real numbers, but all quadratics do. And it has a range from negative infinity up to negative 5. So I know that the a value has to be less than 0 because it's going in the negative direction. And I know my h value has to be negative. Oh, my k value, sorry. My k value has to be negative 5. So y equals an a value bigger than 1. Pick any number you want. It doesn't say anything about a horizontal change, so I'm just going to say x squared. But I'm going to move my graph down 5. There it is. There's an equation that matches those requirements. And it would have to be a negative 3, wouldn't it? The a value has to be a negative number. So negative 3 x squared minus 5 will have a range from negative infinity up to negative 5. And our last one. Create a quadratic function that has a vertical shrink. A vertical shrink is going to be an a value that is less than 1. We could put absolute values around that a. It has to be translated to the left. If it's translated to the left, our h value is going to be negative 8. Some people get confused and they think, oh, I thought you changed the sign. You only change the sign in the equation. If the graph is moving to the left, we need to put negative 8 because that's left. It has the following end behavior. As x approaches positive infinity, the function is going up. Here, the function is going up. So we know that if it's going up, the a value has to be greater than 0. A value is going to be positive. We didn't necessarily know that. And it's going to be between negative 1 and 1. So we can pick a number between negative 1 and 1 that is positive, because that gives us up in a positive direction. The graph goes 8 to the left, so we have to use minus a negative 8. So it's going to look like plus 8. Quantity squared. There is no k value because it did not talk about a maximum or minimum value. And there we have it.